Welcome to the second lecture on the basic processes. Last lecture we covered powder bed fusion process. We also covered directed energy deposition process. We also saw the resolutions what each process can do and which process is cost effective also we saw. Now moving further down, we will try to see a next new interesting process which is binder jetting. As the name itself suggests, there is a binder where jetting will be the process through which it is getting deposited. Here jetting means it is almost dropping. Don't think in terms of high pressure. Jetting means in droplet form a larger flow rate is created. Okay. So binder jet involves 3 steps. First, we manufacture the green part, then we do drying or debinding, and then we do either sintering or infiltration. What is infiltration? Infiltration means you have set of metal powders which are sitting on each other, but in between you see there is a small gap. Now you try to infuse metal into this gap or through this gap for several applications, maybe for lubrication or maybe for thermal benefits. So you try to infuse a different kind of material. So this process is called as infiltration. So a component will be made through green. What is green here? You try to take a metal powder or a ceramic powder, you try to add binder to it so that all these powder particles gets attached with each other. When you try to take the part out, with slight amount of force you can try to break the part. So those things are called as green part manufacture. Then what we do is, so for joining you would have used a binder. Now these binder will be removed from their locations, and here it will not be in such a way such that the powder gets disintegrated. You do that, and then what you do is you do sintering process. First, like powder bed fusion, a powder layer is deposited by a recoater. The binder print head runs over the powder bed and distributes minute droplets of polymer based binder to bond the particles. It is only to bond and create it. Okay. After a layer, the powder bed is lowered by one layer and again it is recoated. This process continues until you get a finished product. Generally, if you are looking for somewhere around about 10 cross 10 cross 10 millimeter big object, it will typically be made by somewhere starting from 1000 layers to 10,000 layers. If you do anything less than that, you get a very rough surface. Staircase effect dominates. So what happens is we try to maintain an optimum of 1000 layers. So for building 1000 layers, it will have to move up and down 1000 times to get the finished part. So this is how the machine will look like. So you can see this is the top view, this is the side view. So you can see here, this is the table where the powder is fed and you try to develop the part. So here you can see there will be a drooping which is happening through this nozzle. So this drooping is nothing but jetting, and in this jet what is getting done is a binder. So generally we use polymer as a binding element. So you look at it, if you want to have multiple composition, say for example you wanted to have mixture of 3 different chemical polymer to generate the best action, that also can be done. or if you want to have 3 different colors, you have basic colors, and then by activating it, when it droops down, it tries to develop and it will try to give the color or the shape whatever it is. So, binder is a polymer material which is done, rest all are very clear here. The material container, then you have ink jet print head. So, you will have a ink jet head. So, here you will have multiple nozzles. These nozzles opening and closing will be done by piezoelectric material or a piezo crystal material. So, it will be very fast. So, it will try to cut down and it will try to make the droplet size very small. So, then you have a recoater which adds material, the part which is getting built, the powder bed, where later you, after the part is made, you suck and remove all the fresh powder for the next operation. Then you will have a overflowing bin also. It's almost like your powder bed fusion, but rather than a laser, here it is getting developed. So, what is the advantage here? The shrinkages which happens can be reduced to a large extent as compared to that of laser. Binder jet machine can regulate the build chamber temperature, which can be used to partially dry printed items. So, we always have a built chamber temperature, which is quite common in fused deposition model when you do with polymers, right. So, there we also have a something called as a built chamber temperature. Here also you have a built chamber temperature to partially dry the print item to prevent slippage when depositing a next layer. So, the polymer will slightly evaporate. The part stays in the machine until the binder is cured. So, after the process, so nowadays what they do is, along with the binder, what they do is they also have, so this is a binder jet, these are the nozzles, and now what happens, now there is a drooping which is happening. Assume that next to the binder jet you have one more laser. This is a UV, deep UV or a blue laser, assuming that. So, this laser tries to interact with the polymer and try to quickly cure it. So, that is done by binder curing. So, a laser is getting attached with a binder jet to produce the output whatever you want. So, here the binding chamber temperature will be regulated to some extent. Since the binder has filled the powder pores, the binder, so that is what, so binder, powder, so this is filled by a binder. So, once you do sintering, you still have 95-96% density, 3-4% will be having pores. Okay. So, that is where we try to do infiltration. So, here the part may be in the machine until the binder cures. So, you can use laser for it to cure. New machines are coming with this add-on feature. Since the binder has filled the powder pores, the product is virtually entirely dense at this stage. It is called green. You can break it when you apply force, but when it goes to sintering, it becomes hard. Next, the green portion are removed from the powder bed, cleaned and removed excess powder and sent to the furnace to evaporate the binder, followed by partial particle sintering. This stage produces brittle, porous green portion. Either the sintering process is extended to close the pores and increase the mechanical quantities, or the green section is infiltrated with bronze or copper to avoid or to fill internal voids. So, I have clearly said distinction between sintering and infiltration, which happens depending upon your requirement. And when the copper is fed in, the copper's viscosity or the bronze viscosity is very important, such that it can try to have a capillary action into it. And having capillary action is also very tough because the pore size are small and it is metal. So, you need to have a negative pressure which is very high. Generally, it does not happen so easily. So, if you are still not able to visualize or understand, assume that you have a sponge which is used for cleaning the table. As soon as you immerse the sponge inside water, you see the water getting sucked into the pores. So, that is infiltration. So, if it happens by free atmosphere, it is easy. If not, what you do is you try to suck it. So, these things are done. The first option shrinks piece, which should be considered during the design itself, because after this you are going to go for sintering. There is going to be a shrinkage, or a shrinkage allowance has to be given. The second alternative shrinks less and can be utilized to make two material parts with Taylor quantities. Binder jet made parts can be beyond 90% densification, although powder bed fusion and DMD are difficult to make with this method. HIP reduces the pore size or the porosity. Binder jet is a good production process for implants or structural pieces that require porosity. So, wherever you intentionally need it, we also try to induce this by this binder jet porous. Porosity can be used for advantage as well as for disadvantage. So, you tune the pores there for your benefit. Porosity can be adjusted by adjusting process factors like powder bed density or binder saturation. This AM technique resembles powder bed fusion and metal jetting. We will see what is metal jetting later. It's similar to powder bed fusion with layered powder. Powder particles aren't fused with heat. Unlike powder bed fusion, they are bounded utilizing a binding liquid. This is economically beneficial because laser and electron beam are expensive and requires severe safety procedures. So, if you are looking for economical way of producing metal additive manufacturing part, binder jetting is one alternative, because you will try to have the process which is done in one place, and then you will have to go to a sintering station next. That is all. So, in between you can try to have a drying station. So, these two does not try to take lot of shrinkage, but here there might be shrinkage. So, all these things have to be calculated upfront before doing the process. The binder is dispensed using a print head similar to that of metal jetting technique, although it only makes up a portion of the part which is evaporated during post processing. Binder jet works very similar to that of your home inkjet printer. Inkjet printer in home, you see there are cartridges. In that cartridges there are binders. So, these binders will do whatever function you want, but glues powder particles together instead of spraying ink on a paper. This technology offers fast printing. So, it is very fast. Today in additive manufacturing, especially in metal, we always look for productivity. So, this process is helping to have higher productivity, the ability to stake parts for efficiency, scalability and print composition. Binder jet is used for visual prototype also. Suppose in this ink, whatever we are trying to talk about, this binder, you can add color also for visualization. When you do sintering, it will go off, but sometimes the color also gets retained, but in green stage if you want, you can use it for visual prototype. Low medium quantity functional parts and big parts with conformal cooling channels for casting and tooling can be made out of binder jetting process. So, this is how the jetting technology, while doing it action, it will happen. So, you will have multiple heads. So, these are all heads, inkjet heads, okay, inkjet heads. So, you will have so many binders drooping down, and then they will try to fall on it and the parts will be done. So, it is very fast process. You also have multi-jet fusion process. Okay. So, in this method, which was created for non-metal powders and later used to metal systems by HP new line of machines, metal jet, two binders are placed on each layer, the fusing agent and the detailing agent. Two different agents are present. One is called as fusing agent The other one is called as detailing agent. So, fusing agent is deposited when or where particles must fuse to produce the parts cross section, that is fusing. Detailing agent is put around fusing agent to define cross section borders. So, two things are important, one is fusing agent, the other one is detailing agent. Fusing for depositing where particle must fuse to produce a part cross section is around the fusing agent to define the cross section. The building platform is then heated. It selectively fuses fusing agent coated particles while leaving the detailing agent coated parts unfused to generate finer details and sharper edges than normal binder jet procedure, and control binder leverages outside the specified part shape. This is a very important point you should understand when we do multi-jet fusing or metal jetting. The selective fuses fusing agent coated particles while leaving detailing agent coated parts unfused to generate finer feature details and sharper edges than normal binder jet procedure. So, this is a schematic diagram for multi-jet fusion technique steps. First, it is material recoated, then you will have thermal control energy which is applied, then you will try to have applying fusing agents, these are fusing agents, these are detailing agent. So, then you will try to expose it to once again temperature. So, fusing is getting done. So, this is fuse, and then whichever this is fuse and unfuse, this is fused, you can see that. So, you try to put the fusing agent, as I told you, will be done through this piezoelectric inkjet nozzle. So, you will have several of these fuses coming down, then you will have details. So, the difference between these two polymers are also there. Okay. So, fusing happens here, and at the other side you do not have any detailing. So, this detailing will try to give you sharp edges, unfused and then fused. This is a very interesting technique. Now, it is gaining speed. So, such wonderful details can be done by binder jetting method. Sample part by using binder jetting technology. Wonderful feature and hollow, voids, everything can be created. So, now let us see the process feature. Is great vertical resolution is attributed to tiny powder layers. So, this is vertical resolution is extremely good, okay, to tiny powder. So, powder size is to some extent proportional to the roughness, to some extent, because later when you fuse it and all these things go up, but to some extent. So, in this technique it is almost proportional. This technology later resolution depends on the droplet size, quality and uniformity on one side and their wetting properties on the other. What is wetting properties? When a particle, when a liquid drops on top of a powder, or let us make a set of powder or a steel sheet. If it is there, when a droplet falls on top of it, now the characteristics of the droplet can be, it is to stay there rolling, or it can go down completely wetting. So, this is the powder or the sheet. So, now here it is just spreading it outside. When the wettability is good, it spreads outside, so that you will try to have maximum contact. When you look at a powder also, you will very microscopically, if you see, it will have surfaces like this. So, when you have surfaces like this, and if a droplet is done, so through these small ridges, the polymer or the binder will be having a capillary action and it can spread. So, that is what we are trying to talk about. Okay. It tries to talk about the quality and the uniformity and their wetting properties on each other. If you have a rough powder and then the viscosity of the binder is also low, so then it can have a capillary action, spread easily. After sintering, so this is green, and after sintering, the resolution of binder jet procedures depend on the layer thickness. Anisotropic correction factor applied to the original CAD model can compensate for the sintering shrinkages. As green components are not sturdy, printed parts with fine detailing like cellular and architectural structure may not be possible, as they may shatter when being transferred to the furnace for curing. So, design freedom is limited when we are trying to look at this process. The printed jet pieces are confined by the powder bed, therefore, there is no need to have a support structure. Big relief. When we do optimization, we also try to do today support structure optimization, which takes lot of time, and many a times the support structure, when you try to break, the component also breaks. So, here you do not need that at all. There is no need for support structure to transfer heat to the base plate. To improve productivity, pieces can be stacked as high as build dimensions and material availability. Binder jet is a high speed AM process because unlike PBF and DED, it does not follow a rastering path, because laser or electron beam, it will follow a rastering path. So, this is the hatch pattern. So, in this hatch pattern, it will follow rastering path, okay, into parallel lines until the part's cross section is complete. Instead, nozzle array bind particles linearly. That is what you saw here. When you saw this, you saw how the inkjet heads are lined and the nozzles, how does it downpour the binder jet. So, one or a few passes of printer head generates each layers. Binder jet is the best technology for economically effective process, scaling up by increasing the number of array of nozzles or the print heads. So, still what are all the big challenges? Though it is very economical, very fast, but still there are a lot of challenges and remedies which are there. It is a complex AM system where numerous factors affect the quality, viscosity, powder, all these things. Even though no beam optical parameters are involved, additional parameters need to be optimized to ensure appropriate bonding, acquire goal porosity level, and maintain geometrical correctness. Even with adjusted process parameters, test layers are frequently needed to stabilize the printing. The fabrication difficulty includes nozzle clogging and poor binder dispensing. Nozzle clogging is a very big feature. So, while printing itself, if the nozzle gets clogged, then all your printer fails. In FDM process, also if you do improper selection of material or the process parameter, then there is always a nozzle clog. Moment there is a nozzle clog, further printing will not happen, the entire part will get damaged. So, binder jet fabrication difficulties include nozzle clogging and poor binder dispensing. Commercial binder jet system commonly include nozzle cleaning, print head health checking stations with automatic cleanings. So, in the system itself, they have a station. After printing, it goes there, and then they try to apply heat. They try to see whether all the nozzles are getting clogged. If so, then it tries to raise an alarm. So, that is what we have. A nozzle cleaning station is there automatically inside the machine. Part shrinkage is an inherent feature of this technique. Evaluate the shrinkage rate during design to ensure the final product fulfillment. The identifying and constructing master sinter curve increases the process complexity and the setup time. So, what are all the materials? Predominantly the binder jet materials are ceramics and polymers, and commercially metallic material are restricted compared to PBF and DED. Binder can treat metals that cannot be thermally processed. As the powder bed based technique, BJ may only use one type of powder. Alloying cannot be done, here it uses only one. Dispensing a binder with specific quantities like electrical conductivity, color, elasticity, etc., or infiltrating components with lower melting point than the underlying powder material can create functionally graded material. This is a challenge, but people have started doing it. X1 offers an annealing 420 stainless steel matrix infiltrated with bronze at a ratio of 60-40, which delivers exceptional mechanical performance, machinability, weldability, and wear resistance. So why I have given you this is you can understand that there are original parts being made for real-time application. So these are some of the products. So BJ increases AM porosity, causes stress concentration, cracking and fatigue failure in BJ made parts compared to the DED and PBF. Binder jetting surface roughness is similar to that of powder bed fusion. HP metal jet technology is recent trial to improve BJ printed sharp corners and well-defined edges. HP has already done. Desktop metal employs printer head that can deposit droplet as small as 1 picoliter to increase dimensional accuracy and surface polishing. 1 picoliter, liter, milliliter, microliter, nanoliter, picoliter. Okay. Since BJ components are not formed by fusing particles with heat, anisotropic characteristics does not induce property non-uniformity in the XY direction. Weak vertical mechanical quantities remains a problem even today. Comparison of traditional binder jetting and desktop metal binder jetting with controlled droplet volume to avoid under and over printing. So this is traditional, this is the shop system which is used. This is traditional binder jetting. So here you see and this you see. So it is capable of printing little more, and it also tries to give you a better performance. So traditional binder jetting and desktop metal binder jetting with controlled droplet volume to avoid under and over printing. So the next process is material extrusion. The process itself clearly says the extrusion will be the principle or the process which is involved in this type of process. So here we will try to extrude material through a nozzle and print it to develop the output. It looks very similar to that of FDM, fused deposition method in polymers. Almost the same thing here we try to do with respect to metals. A wire is used. This wire is made out of polymer and metal. So we mix polymer and metal and then we extrude it and make it into a wire. So this extruded wire passes through a nozzle and then it gets printed on top of a table like your FDM process. Once the print is done, so like last time what you did preheating, here there are machines which has come up with a washing station. So in the washing station what we do is we remove all the polymers and then try to have a green part. This green part further will be placed inside a sintering furnace to produce the final required output. So the first part what we used a binder jet and then metal part addition. Here we mix the polymer and the metal part, extrude it through a nozzle and get the required output. So ME, material extrusion, is a class of AM technologies. This is very much used today because here there is not much of heat induced metal sintering or metal melting. So the thermal induced stresses will not be dominating in these two processes, because once you finish the process then you go for sintering. In sintering you can do a controlled sintering, so you don't induce lot of heat damages, but when you use laser you induce lot of heat damages. Okay. So material extrusion is a class of AM technologies that dispenses a fluidic or semi-fluidic material through a nozzle to build each layer on the part. ME approaches range from a single syringe attached to a XYZ gantry system distributing ingredients using compressed gas back pressure to bioprinter. It is comprised of complex dispensing unit in an environmental controlled chamber to system fed with thermoplastic polymer filament. So, you can use this one or you can use this one. It is ME approaches range from a single syringe attached to a. So, what you are trying to do, metal powder is getting mixed to a liquid and then it is pushed through the liquid. Here when I talked about the FDM process, here it is a solid. Here you can also have it as a liquid. So, liquid you dispense, for example, nano copper powder is dispensed in a polymer. So, it is pushed through. It is allowed to deposit. You try to later do it. So, the fused deposition modeling is utilized by hobbyists for prototyping and industry for high-end products. FDM is preferred ME technology for metal parts. So, it is almost the same. You have a filament spool, one, then you have a main filament supporting, you will have the same in your like your FDM here also. Here the spool whatever we are talking about, this is a metal spool where polymer is mixed. It is a IP process in extruding this wire. It is not so easy. The cost of it will be a kg few $1,000 or it will be $1,500 per kg. So, where is the USP? The USP is here, generating the metal spool. Okay. There will be a spool, there will be a supporting one. So, like your FDM, wherever there is a free hanging structure, the support comes in. The support will be washed in the washing station, and whatever polymer is here, that to some extent will be washed, but rest will be degassed when you do a sintering process. So, supporting filament is there. Then we try to extrude it through the head. This is the extrusion head. Then it is printed. So, the supporting structures for all free hanging structures, we have supporting structures. The entire thing is built on a platform. This is just like your FDM process, but the only difference is here you will have a material which is a metal spool as compared to that of exclusively polymer. So, you can also do the same process, have a syringe or a liquid container or a hopper, and you use a pneumatic pressure to force the liquid metal to come through the nozzle and get deposited. So, there will be a lot of binder, here there is a solid binder. So, you can see here this is the metal wire which is made. So, some companies have developed FDM systems capable of processing metal to benefit this process. So, today we have stainless steel, inconel, titanium, copper, you have mild steel and other materials also we have. And here these machines are expensive because the wires, they are already iterated for the process parameter, and this process parameter is set on the machine to use this for printing. So, it is almost an IP process, and the process parameter selection also is inbuilt. So, the machine as of today is pretty expensive. The metal FDM filament are a metal polymer combination. Without losing powder, handling is very safe here. After printing, the part goes through debinding and sintering steps similar to that of binder jet technique to remove the binding polymer and become entirely metal. So, you can see such small parts can be printed. So, this is a desktop metal studio system is used and they try to print it, and here you can see here how does the material extrusion printer head looks like. So, these are the three parts which are printed. So, the other one is material jetting. In material jetting technology, fluid droplets are deposited on a substrate to make a component. For example, think of it in welding. So what we do, we pass a welding rod is there, we pass a very high current between the welding rod and the workpiece. So the welding electrode melts and it gets deposited. So in the similar way, we try to do material jetting. So in material jetting technology, the fluid droplets are deposited on a substrate to make the component. So multi-jet additive manufacturing is compared to that of binder jet. The material needed to make a part is deposited from a print head. So polymer print head is easy. So here you should have a metal which is liquid and passing through it, and viscoelastic behavior you have to control, and the part is created in an empty space rather than a powder bed. It is just like a bed, and then droplets of the metal comes and does, and you try to control the layer shape whatever is getting done. This method is cheaper than additive manufacturing system using laser and electron beam. The metal jet is a non-contact method that fires droplets at the substrate from a distance, unlike ME. So if you look at it, something like plasma spraying. So there will be a substrate, there will be a nozzle, there will be a plasma which is used to melt the material and then deposit. So adding printed head makes the technique scalable and affordable. This technology can create programmable volume voxel. So this is volume cell. So when we say pic cell, it is picture cell. So it is 2D. This is volume cell voxel, digital material. So the setup looks like this. So this is a material container, and then you have ink jet printing head, then we have a UV curing light, then you get the printed part, then we have a supporting part, we have a binding part. So here this is another technique which is exhaustively used for metal jetting or material jetting. The print material is transferred from the container to the print head. If the target material isn't already a liquid, it must be melted or dissolved or suspended. It is interesting. Heat, or you dissolve and suspend into a fluidic media. So then it can be dropped. Okay. Back pressure then ejects material from the nozzle aperture to produce a droplet. This is an important point which you should record. So back pressure then ejects the material from the nozzle aperture to produce a droplet. A heater attached to the fluid reservoir evaporates the adjacent material to generate a bubble. So to generate a heater is attached to the fluid reservoir. Say for example, this is the reservoir, here is a heater. A heater is attached to the fluid reservoir, evaporates adjacent material to generate. So when you heat it, there is a bubble. So this bubble will try to push, and then you try to get droplets. In piezoelectric jetting, the expansion/contraction of a piezoelectric ceramic driven by an electrical current deforms the fluid reservoir and ejects the droplet. So you have a bubble. So when you heat it, the bubble expands. When the bubble expands, it tries to push it down. Metal jetting printer head deposit material quickly with hundreds or thousands of nozzles to do it. Drop on demand printing releases the droplet as needed. The droplet agglomerates on the substrate and solidifies through cooling. So droplet on demand is wherever you want, the droplet is done. So you heat it, or you have a bubble which expands and pushes the material down. So droplet on demand printing releases droplet as needed. The droplet agglomerates, generally the droplet whatever forms agglomerates on the substrate and solidify through a cooling, solvent evaporation, chemical reaction or photopolymerization. Continue until the component is complete. A solidarity print head prints sacrificial support material. Academic research organizations have developed low-cost MJ system. This system, straightforward assembly, contributes to its widespread use in R&D organization. These organizations have tests, so it is predominantly used in tested, optimized and described MJ polymer, ceramic, composite, functional inks and metals. Printed material is transferred from a container to a print head. The two big companies are Stratasys and 3D Systems have provided high-end MJ systems. The X-Jet is the first commercial metal jet printer firm. Why am I giving all these company names is you should not feel that okay, all these things are still in the research front, it is only in the lab. No, there are machines, there are companies who are using it, there are parts which are produced and they are put into action. So, the next era of additive manufacturing is going to be only metal based additive manufacturing. Okay. In their nanoparticle jetting technique, inks made of suspended metal nanoparticles in liquid media are jetted onto the substrate with supporting material. So, the jetting comes, and here suppose these nanoparticles are used for giving biomedical applications or it is also used for conducting applications. So, on top of a polymer you just eject this and then you try to get it. So, each printer passes through the part which is subsequently removed and sintered to provide the necessary mechanical characteristics. After sintering, 99.9% densification can be achieved in this process. So, this is how it looks like. You can jetting technique is one of the emerging metals. So, you can see these are metal, these are all polymer, this gets deposited so that you get the required output. So, these are some of the gears which are made by material jetting process. So, you can see here these spur gears are made, then surface gears are made. The last process for discussion is going to be sheet lamination. So, as I said, sheet means it is 2D. So, powder you can call it as 0D, wire you can call it as 1D, sheet you call it as 2D. So, naturally when you use powder you will get high resolution as compared to that of wire and 2D. So, 2D is basically a sheet. So, sheet lamination is SL which is used for metals. So, here when we talk about sheets, these are all thin foils or films. Okay, do not think plates will be used. Before solid state joining, these sheets can be trimmed to reflect a layer cross section or extra material can be eliminated after the sheets are linked to generate a particular height. Then we try to use a ultrasonic sonicator to or a bracing binder metal will be used such that the sheet, the one sheet, the other sheet, you try to have some fluid. So, this is the binder. So, this will be ultrasonically vibrated so that it spreads and attaches, or you try to use ultrasonic so that by heat it tries to join. Heat means these heats are very less. Predominantly ultrasonic, what it does is it cleans the oxidation layer, the nascent two material comes in contact, so it tries to join. In this process, two metal sheets are stacked and an ultrasonic tool travels over them to remove the surface oxidation through high friction. Once the surface or the oxidation free layer is done, then the two sheets bind, because you have two nascent layers which bind. Repeated until the near net shape is generated, is done, the final geometry is created and machining will be done to get the required output. This process is done at temperatures considerably below the melting point of the built material. Therefore, it does not change the microstructure or the mechanical property. Important point. Okay. This method can combine dissimilar, important point, dissimilar metal fusion can be done to meet out to the requirements. It can be used for functionally graded materials or for building sensors. Few ultrasonic consolidation compatible material pairs are aluminum alloys can be compared with Be, copper, gold, magnesium, molybdenum, nickel, tin, silicon, tantalum, etc. Aluminum can be mixed with all these things. So, this is how it is. So, first you put the ultrasonic motion causes the oxide layer to break, then localized asperities yield so that it tries to join, and the heat and pressure is attached to it so that you try to get the joining done between the layers. So, these are some of the examples where it has been made. FGM parts have been used by Fabrisonic. So, it is fabrication and ultrasonic. Fabrisonic ultrasonic consolidation system. A part possesses two materials. Smart structures have also getting embedded by using this sheet lamination process. So, points to ponder. So, till now we have studied the most significant or the most used processes in metal additive manufacturing. First one is powder bed fusion, wherein which you use laser or electron beam. Sometimes we also use plasma. Next we saw directed energy deposition, then we saw binder jetting, then we saw material jetting, then we saw material extrusion, and finally we saw sheet laminate metal additive manufacturing process. So, points to ponder is process, material, advantage and disadvantages of all these processes. You are supposed to note it down and write it. Use any reading or open source available material. Try to write down time, strength, roughness and porosity. Keep those parameters as the evaluating criteria and write the process. Then you also write a remarks column for each of these process. So, if you prepare this table, then you will try to understand different types of processes, their capabilities. Now, once you finish this, then you will build one more table wherein which you try to write down the process and different types of materials which can be used for building the output. So, assignment I have already given. So, the one is compare and discuss these additive, then list down various application sectors where we use binder jetting, metal jetting and extrusion application, sheet metal. So, please try to go through this open source available and try to write it down, prepare a table so that it will be helpful for you for the examination. Thank you very much.